recording. Still waiting on the slideshow to start. Wrong. I hit the wrong button. Sorry. Yuck. This could have been a lot faster if I hit the right one. We're on example 9. In fact, I think, now that I think about it, I don't even think example 9 is on this slide set. So yeah, but the next thing we'll cover it. All right, we're recording. We're where we need to be, I think. Let me go back one. Okay, we'll start there. But the other announcements I wanted to make, and I think I made them last time, but some of you may not have been here. I have a doctor's appointment this morning at 11:20. Okay, it doesn't affect this class any, but it does affect my next class because I have to be there at 10:20 for my labs, and that means I have to leave campus basically right at the time class is over, right around 9:35 or so. I think would get me there in time because I got to park and do all that kind of stuff. So I will be leaving here shortly after class, meaning I'm not teaching my trig class today. And you might say no big deal for you. But the other thing is I may not be back from my appointment until right before my 12:30 class. So in other words, my office hours today would normally be 10:45 until 12:30. Obviously, with the appointment being at 11:20, I'm not going to be here basically any of those office hours. Unless they get through in a big hurry, I get back here, but it won't be but a few minutes before my 12:30 class. The odds are I'll be late for my 12:30 class, but they know about it. Okay. So, no office hours today, all that for that. Except for this. I'm going to try to make up my trig class that I missed today on Thursday. And I'll do it right after that class ends, so I'll go 9:30 to 10:45 and then immediately 10:45 to noon. So my office hours on Thursday are also curtailed, shortened to be only 12 to 12:30 because I still have my 12:30 class coming up. So basically no office hours today and only 30 minutes on Thursday because of my doctor's appointment. Now, the other thing I think I told you before, everything is set up in Blackboard. Everything's out there under content, the syllabus, the research paper instructions, my locator card, all the PowerPoints. I think on Tuesday I didn't have all those done yet. They are done now. On Thursday I didn't have them done yet. They are done now. So I think everything's there. I put several sites that either I found or other students have found and said they found them helpful, so they're out there, plus the YouTube videos. There is a link there, and it says Math 112 YouTube videos. When you hit on that, you'll see the 4 classes we have so far, and whenever this one gets up there, it'll be there too. All right? Any questions? Anything we covered so far? Homework? Stuff like that? Any questions? All right. We did finish example 8 last time. Okay? And we were just about to start on example 9. And let me get my pen activated here. Dark purple, or deep purple if you like this music group. All right. Now, Nathan was going to illustrate this for the pass of a baseball, right? Never mind. Okay, this is the example in the text. A batter hits the baseball at a point 3 feet, and we started this one, right? Remember my ugly picture? Y'all aren't supposed to laugh. Okay, it wasn't that funny. Okay. Now, and I won't draw the picture again, but we talked about it. The batter hits a baseball at a point 3 feet above the ground at a velocity of 100 feet per second and an angle of 45 degrees. The path of the baseball is given by this function. F of x is equal to negative 0.0032 x squared plus x plus 3. Just to give you an idea where some of these numbers are coming from, that's at 3 feet above the ground where he hit the baseball. Because what this is telling you, the f of x here, and it says in the plate, is the height of the ball. If I'd have been naming this, I'd have called it h of x. Then it would have been clearer. This is the height of the ball. Okay? What is the x? The x is the horizontal distance. And that's from home plate. Okay, from home plate. So the height of the ball in flight, and the x is the distance from home plate. So when he's standing on home plate, x is 0. How high is the ball then? 3 feet. That's where he hit it, 3 feet above the ground. He hits it with a velocity of 100 feet per second. You really don't see that number here directly. Normally that would be preceding the x here, because that would contribute to that. But actually, that's why this is 32 with 2 decimals in front of it. If you take 100 squared, basically, because you're squaring this x, you'd move the decimal, 100, that would move it 1 to the 1,000. So don't worry about that. This is the equation, okay? Now, Now, will the baseball, here is the question. Here's the batter. I'm not going to draw him fully. Here's the field. Here's home plate, okay? He hits the ball here, 45-degree angle, 100 feet per second. Is it going to clear the fence? Of course, Nathan's would, but we don't know about this guy. And this would be a 10-foot fence. So this is a height of 10 feet here, okay? Now, obviously, my drawing is not to scale, okay? The player here looks like he's almost 10 feet, okay? He's not, okay? The wall is 10 feet, and this fence is located 300 feet from home plate. That's where the fence is, okay? Does it make it? All right? So what does this represent? 300 feet? Distance from home plate. What represents that in our problem? Our x, exactly. And we're asking, is it going to make the 10 feet there? What's that representing? Is the ball that high or not? What does that represent that? The F, okay? So if we plug 300 in here for x, we're going to figure out what the height is. We'll see if it's 10 feet or not. Okay? So let's do it. What's that? Only if you choose. You can do it better than this, though. I don't want you to draw it that ugly. Okay. All right. You don't have to draw it, but I think it's helpful to see and realize what's going on. Okay. So let's plug and chug. The question is, what is F of 10? F of 300, because that is the distance from home plate. What would that be? Negative 0.0032 times 300 squared plus 300 plus 3. Don't forget your plus 3. That might be necessary in this problem. All right. Now, basically, just to let you know, when you hit a baseball with 100 feet per second this way, the horizontal here velocity never changes. And so that portion of it that's horizontal doesn't change. The portion that's vertical increases for a while, but then, the height increases, but the acceleration actually is decreasing because it's pulling the ball downward. Gravity is pulling the ball downward. So it hits at a certain speed, but it's slower, slower, slower until somewhere up here it reaches a 0 vertical velocity. Still going in this amount, and then it starts falling, still going at the same amount this way, but now the velocity is downward because the ball's come down, right? And the question is, does it come down before the fence or after the fence? So that's basically our picture here. So this will be negative 0.0032. And what's 300 squared? 9 what? 90,000. You have to double the number of zeros and square the 3. Okay? 90,000 plus 300 plus 3. All right? Now, I think we could figure it if we wanted to. Minus, what I'm going to do is take these 4 zeros and wipe out those there. So it's just 9 times 32. That's going to be 18,288, negative 288, plus 300, plus 3. We didn't need those 3, but it works. What does that give us? Say again? Where did it come from? Okay. Because I don't have a calculator, I didn't enter it, so I did it, to me, the easy way. Move the decimal, this decimal 3 places, 4 places this way, move this decimal 4 places that way. You're doing the same thing. So, basically, this is 9 times 32. But if you want to punch it in, negative 0.0032 times 90,000. If you do that, you'll find it's negative 288. Right? Okay? Add those together, what you get? Say again? 15. Does it make it over the fence? Home run! Okay, he made it. Okay. Except it was a foul ball, sorry. Sorry, Nathan, never mind. Okay, it did make it over the fence. Okay. Now, they show it in the text, doing very similar to what we did. They also show a graphical solution, okay? And if you have a graphing calculator, which are allowed in the course, would say recommended, but I don't want you to spend the money if you don't feel like you got it, but you could solve it graphically as well. You set up the problem here on the XY axis. It's not really the baseball diamond, but you can picture it that way. 300 feet out there, see what the height is, and sure enough, it's 15 feet. The fence is only 10. And even though he might get a running leap out there, I don't think they're going to be able to get up 15 feet. 10 feet, some of them might be able to do it. If they push off the fence well, they might get it up there. 15, I don't think anyway. All right. I don't think Yao Ming plays baseball. Okay, never mind. So, any questions on that? Now we have yet another application problem. Can I erase this one? Everybody got it? You see why we got everything? Okay. So let's erase all that and do the next one. Okay? Example 10. Alternative fueled vehicles. Now, most of you have your books. If you don't have one, it'd be helpful to look on with someone because the graph is there. And if you think my baseball players look bad, you ought to see my graphs. They're not great. Okay. The number V, where did V come from? Vehicles. The number of vehicles, and this is in thousands, so V in thousands, okay, of alternative fueled vehicles in the U.S. increased in a linear pattern from 2003 to 2005, okay? Now, I will do sort of a graph of it, okay? This is year 2003. They're going to represent that by 3. Then they're going to have a 4. Then going to have a 5, and then a 6, and then a 7, then an 8, and then a 9. Okay, so this is going from 2003 to 2009. Okay? Now, the number of vehicles in thousands are going to vary from, and they sort of have a jiggle there because it's not starting at 0. The lowest number they give you here is 500, and then they're going up to 850. Okay, I'm not going to do all the ones in there, but they're going up by 50. Okay, and somewhere here, this was year 3 was around there, year 4 was around there, year 5 was around there, year 6 was around there, year 7 was around there, year 8 was around there. I'm off some, but you know, you get the general idea. Okay, it follows one pattern for the first 3 years, 3, 4, and 5, and then follows a different pattern 69. And this appears to be pretty close to linear. That appears pretty close to linear, but you don't have one straight line there. Okay? Now, they give this approximation, this isn't exact, but it's approximate, as a function of v. So v of t, where t is time, and this is in years, t in years, okay? And this is number of vehicles in thousands. Okay? So they give this v of t, it's a piecewise defined function. One function for this part, one function for that part. Okay? So this will be, the first part is 29.05 t, where t is the number of years since 2000, okay, plus 447.7, okay? And that's good for year 3 less than or equal to t less than or equal to 5, okay? The second part of this function, the steeper part, is 65.50 t plus 241.9. Okay? And that's good for 6 less than or equal to t less than or equal to 9. Okay. Now, hopefully this makes sort of sense to you. The first top part is good for only those 3 years, including year 5, because that fits. But then year 6 doesn't fit, and I showed it to be too close. It should be a little off here. And it fits that second linear part. Notice the slope here is less than the slope here. Makes sense, right? Now, don't worry about the y-intercepts. They have no real meaning here. But if you stretch this out and put the 0 at an even pace here, then the first one said you'd reach your 0 around 447.7 thousand. But on this one, it's, and of course you see they have a squiggly line here, you'd have to drop this way down here. That would intercept somewhere down here at 241.9 thousand. But we're not worried about that, because these data aren't good for year 2000. They're only good in that domain. That's what we call a defined domain, okay? Explicitly defined domain. It's only good years 3 to 9. The top part 3 to 5, the bottom part 6 to 9. Okay. Now, t represents a year since 2000, so t equal 3 would be 2003, 5 would be 2005, 9 would be 2009. Okay? Okay. Use this function to approximate the number of alternative fuel vehicles for each year from 2003 to 2009. Do we want to do them all? Sure we do, but we're not. Okay, get over it. Let's do 3 first. For year 2003, what would you do? V of, what represents the year 2003? 3. And where would you go to evaluate this? The top part. That would be 29.05 times 3 plus 447.7. Okay? And that would be, multiply that out, that would be 517.8, right? Plus 447.7, and that would be 574.85. It's approximate, because this isn't exact, this is an approximation. So how many alternative fuel vehicles do we expect there to be in year 2003? Okay, actually remember this is in thousands, so that would be 574,000, and this might seem a little strange, 900. Okay, now why did I do that? Well, yeah, because in physics, now the book won't do this, but in physics and in most real measurement situations, this has 4 significant digits, 4 significant digits, 4 significant digits, 4 significant digits. You can't get 5 significant digits out of 4 input. You got to go to 4. So I rounded that last one. Now the book, I'm sure, is going to 85. No, they did 0.9. Look at them. Except I missed mine. 534.9. I don't know. Can't add. Okay. Okay, 534. Sorry about that. 534.9. Not a good morning. Okay, 534.9 in 2003. What would you do for 2004? Same thing, only put the 4 in there. 2005, same thing, put a 5 in there. 2006, go to the next part because that's where that one's defined. So V of 6 would be what? See, 6 is in this portion of the domain, so you use the second part of the function. 65.50 times 6 plus 241.9. So what do we get here? Okay. And let's see. Is it Justin? All right. Still missing the Jones sisters and the Anthony. Other than that, perfect attendance. Way to go, team. Keep it up. I hope they come in. Okay. So if you do this, this 0 goes, and you get a 30 there, so that 0 goes. So that would be a 3 and a 39 plus 241.9, and I think that comes up to be 6, 3, 4.9. But that's in thousands, so there may be 634,900 alternative fuel vehicles that year. Yes, I think they got it right that time. Good for them. Okay. Any questions? All right. They have a checkpoint here, so if you found these a little confusing or not clear, as soon as you can after class, wherever it is, here on campus or at home, wherever, try to do the checkpoint and then the homework exercises. The checkpoints are very similar to what we just did. Now, let me say this too about the YouTube videos. It usually will get uploaded to YouTube, usually, by the time my next class is over with. And if I can have time in my office, then I'll try to get those into the playlist. Today, that's not going to happen, I don't think, because as soon as I leave here, it's not going to be able to upload because I'm going to be taking my computer with me. And until I get to the doctor's office and then have some time, I'll try to get it uploading. Whether it'll upload from there, that sometimes their Wi-Fi is pretty slow, sometimes it's hard to connect. I don't know when it's going to happen. So it may not get uploaded until maybe this evening when I get, well, probably this afternoon when I'm teaching that class. But am I going to have the time to put it on the playlist? No, probably not until this evening. If I have time at home, I'll try to do it then. So don't expect it right away. But in the old Tegrity system, it was out there in 15 to 20 minutes. Yeah.
I have a question.
Yeah.
Like, we just jumped from 3 to 6. If this was a test question.
And I asked for all of them?
No, you're
Oh,
okay.
okay.
Not going to ask for all.
Oh, thank you. I was going to say you can throw things at me.
Ones you wanted, like 5,
Right.
8, and 9.
Right. Well, yeah, I will. Yeah. Yeah.
Okay.
I was just showing you how to do each group.
Okay.
And then you just,
Okay.
for 7, 8, and 9, you do it the same way you did this
Right.
one when you play 7, 8,
But
and 9.
you would tell us which
I
one.
would say, yeah.
Okay.
In fact, I'd just give you one question.
Thank
What
you.
is it for those? More than likely. Never mind. I didn't say that, did I? Okay. All right. The last topic. Any questions on this before we move on?
I got it.
Okay. It's just how to plug in functions, evaluate functions. Okay, this is the stuff from the last example that we've already done. All right, now we move to different quotients. Are y'all familiar with these at all? Yay or nay? No? Okay, I bet you're familiar with the words though. What do they mean? Say again? Subtraction and division. That's exactly what they mean. Now, what do we mean by that? And believe it or not, you are familiar with them whether you realize it or not. Okay? Now, they'll make it look confusing, but it really isn't. One of the basic definitions in calculus, this is pre-calculus algebra, it's getting you ready for that, is this definition here. Now, that might look totally strange to you, yay or nay? Yeah, okay. But guess what? It really isn't. Okay? And here's why. What is f of x? See if you've learned anything in this course so far. Y, exactly. So f of x plus h would be some other y. This would be your first y, this would be another y. H further on from x. So you have x here, x plus h here. This is f of x, this is f of x plus h. Right? The y on the second value minus the y on the first value. Right? Now, what is h here? Difference between x plus h and x. Because if you do x plus h minus x, what do you have left? H. And haven't you done change of y over change of x before? When? Slope. Yeah, that's exactly it. You've done a slope before. If you did a slope, y2 minus y1 over x2 minus x1, you did a difference quotient. This is a difference, this is really a difference, and there's a quotient. You've done a difference quotient. So it's not that new, is it? You've seen it before. Now, what's true about this? This h cannot be equal to 0, obviously, right? Because you can't divide by 0. Now, later, if you go on to calculus, I hope many of you, I wish all of you did. It's such a fun subject. But if you did that, you'll find out that you can still do something if you're dividing by 0 if your numerator is also 0. That's called an indeterminate form, and that may actually have what they call a limit, which would be a derivative. Okay? That ratio is called the difference quotient, illustrated in this next example. All right. Find 4 f of x equals x squared minus 4x plus 7. Find your difference quotient. F of x plus h minus f of x divided by h. Okay? Now what do you reckon you need to figure out first before you can do the difference quotient? Say again? The h. It's just the letter h. Don't worry about that. It's just h. Leave it as h. Say that again. Okay, no, we're not even doing that. We want to know the difference quotient, whatever the x's and h's are. Okay, you got to plug something in, and what you have to plug in is this. You need to figure out what f of x plus h is. And how do you do that? Plug it in everywhere you see an x up here, you put in, set in place of it, x plus h. So this will be x plus h squared minus 4 times x plus h plus 7. Okay, we got a little work to do, but it's not bad, is it? How do you square a binomial, x plus h? There's 2 different ways. Yes, very good. What he said, I think, was square the first, x squared, twice the product of the 2, x times h would be xh, double that, plus 2xh, and square the last, plus h squared. Now, if you didn't remember that, you can always go over to the side and FOIL it. X plus h squared means x plus h times x plus h, right? That's what it means to square something. Multiply it by itself. And now you FOIL it, and what's the first thing you do? Square the first, x squared. What's the next thing you do? Outer, which is plus XH. Inner, which is plus XH. Guess what? That's double the XH. Double the product. Okay? And then the last you do is a square the last plus H squared. So that's the same thing you got here. This is a little quicker if you can remember that rule. If not, always go do, and you've got a smiley face. Okay. Okay. Now, let's go to the next term. What will that be? Minus 4x minus 4h. I used to be in that, by the way. Plus 7. Okay, is there anything we can do to simplify? I don't see a thing that we can do to simplify. Can you? So that's our f of x plus h. Now we take that and plug it into our difference quotient. That's the first part of your numerator here. So that's going to be x squared plus 2xh plus h squared minus 4x minus 4h plus 7. Whew. Minus, what's f of x? That's the first. That's what they gave you here. So you put that. Now, since you're subtracting, be sure you put that in parentheses. You don't just put a minus and start writing. Put a minus and put it in parentheses. X squared minus 4x plus 7. And you're going to do what with that then? Divide by h. Okay? Now, let's go back to the numerator. I get tired of writing this, but it's fun. X squared plus 2xh plus h squared minus 4x minus 4h plus 7. Okay, now distribute that minus sign in. What does that give you? Minus x squared plus 4x minus 7. Okay, get out of there. Okay. There's your numerator, and it's divided by h. What can you do with that numerator now? Combine like terms. Well, I do have another x squared. Here's an x squared, and there's a minus x squared. They add to 0. Now, I don't have a xh term anywhere else, so I can't do anything with that. I don't have another h squared term. I can't do anything with that. But here I have a minus 4x, and a plus 4h. Those add to 0. Wow. There's no more h terms, so you leave the minus 4h there. But you do have a plus 7 and a minus 7. They add to 0. Look at that. What are you left with in the numerator? 2xh plus h squared minus 4h, and you're going to divide that by h. Now, guess what you can do to that numerator? Factor out an h. There's an h in each term, common factor. Factor that out, and that leaves you with what? 2x plus h minus 4. And you divide that by h. And now what can you do? Now you can let the h's divide away. Here is your difference quotient. 2x plus h minus 4. Now, are any of you planning to go into calculus? Please somebody say yes. Right? Oh, fantastic. Fantastic. Okay. Now, what we'll do in calculus then, like I said, in calculus, what we then do is take a limit as this h gets closer and closer to 0. Well, we can't let it be 0 when it's in the denominator, but look what we did. We got it out of the denominator. So what can we do now? We can let that h go as close to 0 as we want to. And what is your answer going to be? 2x minus 4. You know what that's called? The first derivative of that function. Later, after you practice this a little bit, there's a rule you can use. 2 times x, drop that by 1, minus 1 times 4. 4, drop that by 1, 2x minus 4. Exactly what you have here. It's all taking the derivative of a polynomial function. And we just did it using the difference quotient, which is actually what a derivative is. Okay? So, that's us doing it. Let's see how they did it. Okay? We'll erase all that ink. Any questions on it before I erase it? Okay, good deal. All right, first thing they do, figure out what, well, they write it all out. You can do it this way if you find it easier to see. But they first calculate what alpha of x plus h is x plus h squared minus 4 times x plus h plus 7. That's what that is. Minus alpha of x, so you put the alpha of x in here, minus that. We did that too, we did it in a later step. Divide by h. Okay, first thing we're going to do, square that binomial. X squared minus plus 2xh plus h squared, that's that one. Minus 4x minus 4h, that's that one. Plus 7 minus x squared plus 4x minus 7, that's that, divided by h. Next, they combine like terms and lose a whole passel of them, and all they are left with 2xh plus h squared minus 4h divided by h, and from that you can factor out at h, and that's what they did. H times 2x plus h minus 4 over h. The h's divide away, and that leaves us 2x plus h minus 4. As long as h is not equal to 0, but you can allow x to get as close to 0 as you want to, and the closer h gets to 0, the closer this gets to 2x minus 4. And that's going to be your ultimate limit of that function. Good deal.
Do we need to put it over h, or are we fine with how it's changed?
What's that again now?
Do we need to put it over h?
Over
or are
h?
we fine with what we had?
Okay. Yeah, I mean,
No, I'm saying our answer.
our answer was not over h anymore because you divided them out.
Right.
Yeah.
Okay.
So once you divide them out, don't put it there anymore, right? Okay. That is your answer. Now, whether you put the h not equal to 0, I really don't care that much about that, but it's true. Because it was true at the beginning, it's true here. It's just that it doesn't have any problem here because you don't have h in the denominator anymore. Okay? Good deal. Guess what? There's another checkpoint. I would definitely take a look at that as soon as you can after class. Now, here they give a summary of this function terminology. Pretty important stuff because we're going to be using these terms all term long. Different kind of term. Okay. A function. Function is a relationship between two variables such that to each of the variable, the independent one, the one first, there corresponds to only one value of the dependent of the second. This is x, y, a, b, whatever it is. The first one, for every one value there, you only can get one value of the dependent variable. Your function notation, most important thing I think to remember about functions, y is equal to f of x. If you remember that, basically you can remember you got most of the course in that handle, if you think about it. F is the name of the function, like Fred or Sue or something like that. Y is the independent variable because, y is the dependent variable because it depends on what value you put in for x. So x, you put in anything you want to, that's your independent value, okay? That's like the cheerleader saying, give me an x, okay? So that's the independent value. Once you do that, go team, whatever, okay. Now, x is independent, y dependent. F of x is the value of the function evaluated at x, which is the y value. F of x is equal to y. The domain of a function is a set of all those values or the inputs of the independent value for which the function is defined. What functions are not, where do we run into definition problems of functions? Two cases that we've run into so far. Anytime you have a variable in your denominator cannot be 0. If that variable is down there, you have to exclude any values in that domain that would make that denominator 0. What's the other case? In the radicals, what can you not have inside a radical? You cannot have a negative number. So everything inside the radical has to be greater than or equal to 0. What's that? If it's an even root. If it's an odd root, you have no problem at all. Anything can go in there. Okay. So that's said to be defined at that x. If x is not in the domain of f, then f is said to be undefined at that value of x. Like dividing by 0 or taking square roots of negative numbers, you can't do it. The range of a function is a set of all the values or the outputs assumed by the dependent variable, that is the function values. Usually those are put on the vertical axis, the horizontal is your domain. Now, we have explicit domains, like that problem we did just a few minutes ago, where t was 3, 4, 5, 6, 7, 8, 9. That is an explicit domain. That's the only values you can have in that domain for that function. okay? But you have implied domains. If f is defined by an algebraic expression, domain is not specified, they don't tell you exactly what it is, then you have to imply the domain, and here's where you start. Where? You assume all real numbers unless there's any that you have to exclude. Okay? If they don't tell you the domain, use an implied domain, all real numbers for which the expression is defined. That means no values that would make a denominator 0 or would make a square root or an even root negative. With one other exception. If you have a real physical problem, okay, and you have something like time, guess what? There's no such thing as negative time. You start now and go ahead. You don't ever go back. Back to the Future was a movie, but that was all. It was just a movie. Okay, and lengths, you don't have negative lengths. Okay, you don't have negative distances. Okay, so things like this, radii, you don't have a negative radius. You don't draw a circle with a negative radius. So those kinds are also implied domains. If physically you know it can't be, then you exclude those as well. All right. I think that's the last slide in the set. Let's look at the vocabulary, top of page 44. Fill in the blanks. A relation that assigns to each element x from a set of inputs, and what's that set of inputs called? Domain, or domain, exactly one element in y, the set of outputs, or range, that's called a function. If it assigns only one value to the range, that's a function. Number 2, for an equation that represents y as a function of x, the set of all the values taken on by the blank variable x is the domain. What do we call that variable? Independent variable. And the set of all the values taken on by the blank variable y is the range. Dependent variable y. Excellent. Number 3, if the domain of a function f is not given, then the set of the values of the independent variable for which the expression is defined is called the blank blank. Implied domain. Very good. In calculus, one of the basic definitions is that of a blank blank given by f of x plus h minus f of x divided by h as long as h is not equal to 0. Difference quotient. Perfect. Okay, I've given some of these before. I'll repeat them now. Either the odds 5 or 7 or both. Do number 9. It has 4 parts. Do any of the odds 11 through 19. Any of the odds 21 to 31. Either 33 or 35 or both if you choose. Any of the odds 37 to 43. Either 45 or 47 or both. Either any of the odds 40, and this is, any of the odds 49 to 59. And then on some of the application problems, any of the odds 61 through 73. No, make it 75. 61 through 75. And I think I would be judicious in those. They have 2 geometry problems. I'd say maybe do one of those, that kind of stuff. Or they may have more than 2. But anyway. And if you're, say, a business major, maybe those cost functions or median sale price, something like that might be the ones you might be more interested in. If you're going into pharmacy, the prescription one may be. So you pick the ones that make the most sense to you. And do a few of the others if you like. And then under the difference quotients, any of the odds 77 to 83, and then either 85 or 87 or both. You get to choose. Now the exploration, you don't expect to see many true false on any test. I don't usually give those. I don't really like true false questions. But it's still a good idea to read through these and see if you understand what they're getting at. It is a good study tool, okay? And I think the odd answers are in the back there too. There's a think about it, which is a good thing to do. but you don't have to write those up if you don't want to. Okay? Any questions? 1.4. Okay? Yeah. Any of the odds in every group. You can do them all if you want to, but if you zoom through them and say, hey, I did the easy ones, I've done the harder ones, I'm going to skip the rest. I'm going on to the next group. That's what I suggest you do. Yeah. Don't get by. Hey, we're not through, folks. We're through with that section, but there's 1.5 to come, right? Yes. I don't want to cheat you out of a penny of your tuition dollars here, okay? All right. I hit the wrong key there while I was making dumb comments, okay? So I have to, well, let's see if it's going to do. Okay, here we go again. All right. Okay, 1.5. We'll at least get started here. We got plenty of time. Okay. All right. We're going to start at current slide. All right, continue with functions and their graphs. We will now analyze the graphs of functions. Okay? The various objectives here. We will use the vertical line test for functions. Have y'all done that before? Good. Find the zeros of functions. Have you done that before? You may have not realized it, but yeah, we'll do that. Determine intervals on which functions are increasing, decreasing. Determine relative maximum or relative minimum. Done that before? Maybe, we'll see. Okay. Determine the average rate of change of a function. I bet you've done that and you don't even realize it. And we'll identify some even and odd functions, what makes a function even or odd. And actually, there's another classification. The neither function. Neither even nor odd. In fact, most functions probably will wind up being that. So let's first look at the graph of a function. Okay? We've studied functions from an algebraic point of view, which I think is pretty fun. In this section, we'll study graphs from, functions from a graphical perspective. It's fun too, right? The graph of the function f is a collection of ordered pairs, x, f of x. Now, what do we used to call our ordered pairs? X, y, but guess what? F of x is equal to y. There it is again, okay? X, f of x, such that f, x is in the domain of the function, okay? And that's what we're going to be looking at. Now, we may not do them all. If this is a continuous function, it may have an infinite number of points between here and there. I mean, just in the smallest things, infinite number of points in there. Two pixels on the page is an infinite number of points in between those two pixels. I mean, it's incredible. So we won't do them all, but we'll do a few represented, and usually we'll connect the dots in like you used to do in drawing. Okay. As you study this section, remember, x is the directed distance from the y-axis, right? 1, 2, 3, 4, yeah. Directed distance from the y-axis, where y, or f of x, is the directed distance from the x-axis. Here's your y here, or here's your f of x here, okay? So, keep that in mind. That hasn't changed. You've done that before, right? Okay. Now, here's example 1. Use this graph of this function f, this is the function f, to find first the domain of that f. That is your function f. What is its domain? Say that a little louder. 10.025. Okay. Pretty close, but not quite. He gave me that, and this. Okay? But guess what? Every point in between is also in that domain because they connected the dots here. So let's go back and revise that. From -1 to 5. Okay, now how would I write that? There's two ways you could write that domain. Let me get my pen back to dark. Okay. I could write that in set notation. The domain of f, that's how I call it, the book doesn't call that, would be the set, that's the set notation, it's called a brace, of all the values, and this is x, such that, then what would I write here? So let's start with -1 is less than, x is greater than, -1 is less than, or equal to, very good, x, no, less than, strictly less than. That's why I had to write it out. Notice you have an open circle there. You don't include the 5. That point is 5, too, but the open circle means it's not in the function. So that means you go up to 5, but you don't include 5. So that's how you write it. That's how you would distinguish it. That's your domain. Give me that in interval notation. -1 to 5. Parentheses around 5 and bracket on 1. Bing, ding, 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 ding. You got it. There's your domain of F. You count the -1. You don't count the 5, but you count everything in between because all those points are covered. Okay? So that's the A part. B part. You tell me the function value F of -1. What would that be? F of -1 is not -1. 1, exactly. There it is. There's your x. There's the y corresponding to it, or your f of y. Okay? How about f of 2? What would it be? Say again? -3. Perfect. Now give me the range of f. How do you want to give it to me? Set notation or interval notation? Say again? Interval, okay? Tell me how to begin. Start from the lowest. Bracket -3, comma, 3, bracket. Perfect. Give it to me in set notation. The set of all real numbers. What real numbers? Y, such that, start with the little one. -3 or equal to, y is less than or equal to 3. +3. You got it. Okay. That's the range of F. Okay? Now remember my little visual. You may not like it, but if it's helpful, use it. For the domain, shine a bright light from somewhere way above it on this, and the function blocks the light shines on the rest of it. So all the portion of the darkened x-axis, that would be from -1 up to, but not counting 5, because the light comes through at 5. So that would be your domain. Your range, shine the light from one side or the other, and it would be shadowing everything from -3 to 3. Everything else is included. Make sense? Okay. Any questions on that? Let's see how they did. Okay? The closed dot at -1, 1 indicates that x equals -1 is in the domain, whereas the open dot at 5, 2 indicates that x equals 5 is not in the domain. So therefore, the domain of F, that F that they gave us, was the interval from -1 to 5. Yes. That's too slow. No, I'm just kidding. Go ahead. Okay. The bracket is when that point is included. The -1 is included because that was a dot. The 5 was not included because that was an open circle.
Okay. So
That's when you do.
in a parentheses.
Say again?
That's why you use a parentheses.
Yeah, the parentheses means the 5 was not included. The bracket means it would be 4.99999999999. How many nines you want to write? No. You can't write them all. No. So just do 5 and don't count it. Yes, that's it. You got it. That's what it does for you. See, mathematicians, they'd be a little lazy, right? Yeah. Don't write all those nines. Okay, yeah. Good deal. There's your domain. They wrote it in interval notation. The book loves interval notation, by the way. Now, because negative 1, 1 is a point on the graph, it follows that f of minus 1 has got to be positive 1, because the function maps whatever your first is onto the second. So that would be that one. Yeah. Similarly, because 2, negative 3 is a point on the graph of f, it follows that f of 2 must be negative 3. Go across to 2, find the function, up or down. It happened to be down. Its y value there was negative 3. F of 2 is negative 3. Y'all got that right. And the c, because the graph does not extend below f of 2, which is negative 3, or above f of 0, which is 3, but it does include both points, the range is the interval from bracket negative 3 to 3 bracket. Good deal. Those are both solid circles there. Any questions? Y'all got it right. And by the way, there's a checkpoint. Do them. Okay. In fact, that's an unusual one. Take a look at that checkpoint. Okay. And I can't show it on the graph, and some of you, if you don't have books, you have to look on with someone else. But notice there the function extends past negative 3, 6, negative 6, and it extends past 3, negative 6. So that implication is that function goes all the way to infinity. The x's go to infinity. The y's, however, only go up to 3, but they go from negative infinity up to 3. But what do you notice about the domain? It does not include negative 3. So the domain would be from negative infinity up to negative 3, parentheses, union, parentheses, negative 3, and then all the way on to positive infinity. You have a hole in the graph, and that's how you designate it. Okay. Interesting, they gave you, that's a little more difficult than the one we did. All right, let's move on. By definition of a function, at most one y variable corresponds to any given x variable. So guess what? You pick any x in your domain, and when you're looking for y's, how many do you look to find? One and only one. It might be up here somewhere, down here somewhere, but it can only be one. If there's more than one, not a function. This means that the graph of that function cannot have 2 or more different points with the same x coordinate, which means no 2 points on the graph of a function can be vertically above or below each other, right? So therefore, it follows that if a vertical line is drawn through the graph of a function, it can only intersect no more than once. Yeah, it may not have one, but it can't have 2 or more, right? It can have no more than one. That's it. So that means here's a simple way to identify on a graph whether it's a function or not. Observation provides a convenient visual test called the vertical line test for a function. Set of points in a coordinate plane is a graph of y as a function of x if and only if no vertical line intersects the graph at more than one point. If it does, not a function. Okay. Boy, they got through that in a hurry. Let's look at example 2. I'm not going to draw it, but hopefully you can see it. This one here, nice looking parabola here. Is that a function? No. Now over here, it intersects only once. Over here, it doesn't intersect at all. No problem there, but anywhere over here, vertical line intersects twice, not a function. How about this squiggly thing? Could that be a function? Yes, it is, because the vertical line intersects more than once. Horizontal lines, we haven't said a thing about them, only vertical lines. Okay? Later we'll talk about horizontal, but not yet. How about this one? It has a hole in it. It is a function. It's just not defined in between 0 and 2. But it's defined everywhere else, and then in those places it only intersects once. So the first one is not a function, second one is a function, the third one is a function. Very good. All right, there's a checkpoint there too. I'll let you do that on your own. Do we have time for zeros and functions? We can define it anyway. And we already did something like this, remember, in the first set of homework exercises. If the graph of a function of x has an x-intercept at a0, a can be anywhere on the x-axis, but if that graph crosses at a0, then a is called the zero of the function. So how do we find it? The zeros of functions. Zeros of a function of f of x are the x values for which f of x is 0. The zeros of the function. Set the function equal to 0. Any of the x values that make that true, those are the zeros of the function. We did that algebraically in section 1.4. Now we're doing it graphically by picking up those x-intercepts. A0. Right? All right. Here's example 3. I think we can get the first one done, can't we? No. Oh, y'all are even fun, okay? All right. We'll start there with example 3. That's where I started last time I taught this. So, let me find my... I did have some papers in here. I don't know where they are. I'll use one of these. Okay. Homework exercises in 1.5. Okay? Do either 7 or 9 or both. They have 4 parts each. Do either 11 or 13. Okay? And we'll stop there and pick up from there next time. All right. I will be leaving campus probably within 15 to 20 minutes. So if you need to see me, that'd be a good time to catch me. But I won't be back until probably awfully close to, and maybe even after 12:30. And then I have a class that goes until 5 o'clock. So not many office hours today. Good deal. Hope you don't mind me using you in baseball, do you? Do you mind me using you? Huh?
I'm in Mrs. class this semester.
Yeah, you got some games. Yeah, okay.
I'll let you know.
Okay. Yeah, okay. All right, good deal. Okay. Oh, we missed our Akira. Missed her too. Is that 4?